Okay, let's get started. Hello, everybody. Thank you for joining us and welcome to the ASTRO 3D ECR Astronomers in Australia seminar series. My name is Dr. Amelia Fraser-McKelvey. I'm a postdoc at the University of Western Australia as part of ICRA, and my co-chair today is Dr. Dorota Bayer, and from the Swinburne University of Technology. So before we begin, it's important for us to acknowledge the traditional custodians of the land on which we meet today. The Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing traditions of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. I'm speaking with you today from the land of the Whadjuk Noongar people. My co-chair Dorota is joining us from the land of the Wurundjeri people of the Kulin Nation. Our first speaker, Daniel Prole, is speaking to you from the land of the Watamatagal clan of the Darug Nation. And our second speaker, Christina Martinez-Lumbia, is speaking from the land of the Bedegal people. We pay our respects to their elders, past and present, and extend that respect to all First Peoples joining us here today. So why are we here? This series is facilitated by ASTRO 3D, which is the ARC Centre for All-Sky Astrophysics in 3 dimensions. COVID-19 has affected our ability to travel and present at international seminars this year. Especially for us in Australia, the time zones mean that often meetings take place at 2 or 3 in the morning. Case in point, it's currently 4 a.m. for me. This lack of opportunity to network could disadvantage junior astronomers when entering the job market. This series aims to combat these issues by providing a platform for junior astronomers to present their work to the world. Just a bit of housekeeping before we begin. There's going to be 2 talks over this hour. Each talk will be 20 minutes in length with 5 minutes for questions at the end of the talk. Please save your questions until the end of the talk, and you can feel free to use the chat function to type your question in if you would rather Dorota read it out for you. The talks are being recorded and they're going to be placed afterwards on the ASTRO 3D YouTube channel. By being here today, you're agreeing to abide by ASTRO 3D's meeting code of conduct. I've already warned the speakers of this, but because of Zoom, I will need to interrupt them with 5 minutes to go in their talk. So let's get on to our first speaker. Our first speaker today is Daniel Prole, who is a postdoc at Macquarie University in Sydney. Daniel will be talking to us about the field population of ultra-diffuse galaxies. So Daniel, you can go ahead and screen share. It's all yours.
Yep. Hi, everyone. I'm Dan. Here we go. Great. So can everybody see the screen?
Yep, looks great. Okay,
cool. So yeah, I'm Dan. I'll be talking about the field population of ultra-diffuse galaxies. This is work in collaboration with Remco van der Berg, Michael Hilke at ESO Garching, John Davis at Cardiff University, where I did my PhD, and Lee Spittler at Macquarie University. Okay, so what are ultra-diffuse galaxies? Well, I'm sure a lot of people may be familiar with these things already. Essentially, they're large dwarf galaxies. And because they're so large in terms of their physical effective radii, they also have characteristically low surface brightness levels. One of the puzzling things about ultra-diffuse galaxies is the fact that they show such a wide range in physical properties, such as the halo mass. So these are 2 relatively famous ultra-diffuse galaxies, DF2 and Dragonfly 44. They look fairly similar. They have very similar sizes and stellar masses, around 10 to the AM0, but they have a huge difference in their estimated halo mass. DF2 is this galaxy which is thought to be dominated by its stellar mass, so it has very little dark matter, whereas upper limits in the estimates for DF44 show it to be around the same mass as the Milky Way. So explaining these wide-ranging properties is very difficult, and so a lot of people have put a lot of work into galaxy formation models to explain these things. As an aside, these galaxies were actually first discovered with the Dragonfly telephoto array, and this is a telescope which is optimized for imaging in the low surface brightness regime, where you really have to minimize the amount of light in the focal plane. I'm working at Macquarie on a very similar telescope called Huntsman. and we've just started taking commissioning data. So if you're interested in this, feel free to ask me questions at the end, or even look at the control software or the data reduction pipeline, which is all available open source online. Okay, so when thinking about these low surface brightness galaxies, I always like to look at this plot. And this plot is taken using the Gamma Spectroscopic Survey, published by Wright et al. And actually shows the distribution of gamma galaxies in terms of surface brightness and effective radius. Stellar mass. And shows the gamma sensitivity window in the orange box. And essentially what this is showing is that for galaxies with average surface brightnesses within their effective radii less than around or greater than 24 magnitudes per square arc second, essentially gamma is completely insensitive to these things. But also this translates into a significant bias in terms of stellar mass. So maybe even most galaxies below 10 to the 9 m0 in stellar mass will be of low surface brightness. And this is something that's supported by theory as well. And so this means that even in contemporary spectroscopic surveys, we really do not have good samples of low surface brightness galaxies. And this translates into a distance problem. We have no distance information to a lot of these things. This doesn't really affect UDGs and low surface brightness galaxies in nearby galaxy groups and clusters like Coma, Fornax, and Virgo, because they can be relatively easily identified by the high number densities and relatively large apparent sizes. But you can't use the same arguments to identify these things in the field. Again, because you can't differentiate between them and, for example, background galaxies easily. Therefore, most of what we know of these things comes from these kind of high density environments where we're more susceptible to tidal effects, which may be in part responsible for producing these large low surface brightness systems. So in order to try and get around these problems, we can try and do some statistical analysis to look at the overall population of UDGs in the field. So in the field is kind of like in isolation outside of galaxy groups. So the first thing I'll address in the talk is whether there is a UDG population in the field at all. In fact, whether there is a cluster-like population of UDGs in the field at all. I'll come on to that in a minute. But there is theoretical evidence to suggest that these things should exist in the field, that they form through secular channels like supernova feedback, as well as these environmentally driven processes. But in the field, you would expect the secular channels to be the dominant evolutionary channels. We do know that some of these large low surface brightness things exist in isolation, thanks to H1 surveys. But this really only gives us an indication of the H1 rich population. We don't know that much about the overall field population. One interesting thing about UDGs in clusters and groups is that they are actually quiescent. They're quite red. And you know, they wouldn't necessarily be picked up by these H1 surveys. So we can ask, does this population of cluster-like quiescent UDGs exist at all in the field? So to do this, we've used the KIDS data. So that's the kilodegree survey. It's a VST optical imaging survey. And it's characterized by a fairly uniform and high quality data reduction quality over its very large footprint. So it's thousands of square degrees in the final data release. However, it's not as deep compared to other contemporary surveys like HyperSupremeCam, DR1 at least. So in DR1, it's around half a magnitude deeper than KIDS, but the data reduction quality is not as clean. So we don't actually do source detection using HSC because it leads to a lot of spurious detections. Actually, we use KIDS for source detection and structural parameters, and then go to HSC to measure colors because it's that much deeper. So there's a cartoon image here of the source extraction process. We use a software called MT Objects, which is a alternative to source extractor, which handles low surface brightness objects better, particularly in terms of deblending them and flux estimates and things like that. We then run parametric fitting using GalFit over the top to try and really constrain their structural parameters. And then we use these GalFit models essentially to select our final sources. So the reason we're using GalFit is that segment statistics alone are always biased, particularly when you're looking at things in the low surface brightness regime. So here's a plot showing essentially the intrinsic effective radii of a bunch of synthetic source injections into the data versus the recovered estimate just from the segment statistics of, it's not just empty objects, this is common to all kind of source extraction algorithms, including source extractor, and shows there's this huge bias. You really underestimate the recovery, the effective radius. And this actually translates into overestimating the average surface brightness and the effective radius. So it's a big problem. So that's why we use GalFit. It's because it does a much better job of actually removing that bias when you're measuring low surface brightness sources. In fact, we're doing single Cerseic fits, and by which generally do a pretty good job of describing these UDG-like galaxies. When we do the synthetic source injections, we are able to recover the structural parameters with high precision. And again, this is based on 1 million galaxy injections. We're also able to measure the recovery fraction as a function of surface brightness and effective radius. And in comparison with other works, for instance, Van der Berg in 2017, who looked at the same data with source extractor, we're able to go around half magnitude deeper. And that's probably attributable to empty objects. So for this part, our final sample consists of around 200 galaxies. We don't know any distances, again, so this is going to be a recurring theme. So we can look to the literature and in particular to empirical scaling relations for ultra-diffuse galaxies, such as the size distribution, the mass formation efficiency, so how many UDGs exist per unit available mass, as well as their color scaling relations. So again, in clusters, they're quiescent. And you can basically create this model, which you can sample, or you can evaluate the model and try and predict, again, accounting for the recovered fraction of sources, what the distribution of color you'd expect to observe would look like. And this is done in absolute number, because again, we have a very first order estimate of the amount of mass within the area that we're looking. That comes from basically theory. We have a very first order estimate of the mass formation efficiency. So to first order, we can predict the absolute number of things that we'd expect to observe, as well as their colors. Now, if you take this quiescent model and you sample it and compare it to the observations, you find that essentially the two peaks are offset. So this is in the left panel. And this means there are not enough large red low surface brightness galaxies in the local volume to suggest that this quiescent population is forming with anywhere near the same mass formation efficiency as it does in clusters. So there is robust evidence for absence of this population. You can then play around with the model if you want and adopt a slightly bluer color model. And this does actually a much better job of reproducing the observations. And this is kind of very tentative evidence there might be this kind of bluer field population with maybe even similar mass formation efficiencies as would exist in the field. So this kind of motivates the second part, which is what is the quiescent fraction of LSBs in the field, or like UDGs. So in part one, we show there isn't this large quiescent population, but we do know that some examples of quiescent UDGs do exist. There are only a handful of confirmed examples, maybe even 2 that I'm aware of. And this, is offering us some insight into how efficient secular processes are at quenching these kind of galaxies. And this is a direct testable from galaxy formation theory. So this time, this was about a year after that kids project, we can use the second data release of Hyper Supreme Cam, in particular the R band. So this is actually much deeper than the kids data. And the great thing about DR2 is A, the footprint is larger than the first data release, and B, the data reduction quality, in particular the background subtraction, is of much higher quality. So you can see the comparison given in AHARA 2019 of the background subtraction working in DR2 over arc-minute scales, and this is really good. And for the kind of galaxies that we're looking at, this means that we can get away with making pretty good measurements of sizes and things like that without having to worry about the background subtraction. Also critically, we're using overlap with the gamma spectroscopic survey, and this is because we use spectroscopic galaxies as a way of inferring distances. I'll come on to that later on. So yeah, our source extraction process is very similar to in the first part of the talk. We use empty objects again, but this time using PyInfit, which is a slightly more efficient, it's a bit faster than galfit, and it works a little bit better if you're in Python. Again, using these single SOSIC profiles. This time, again, we're targeting kind of relatively large in terms of their apparent sizes, galaxies, as well as low surface brightness galaxies, but we're able to go around magnitude deeper compared to the Van den Berg survey. And this is down to the deeper data, mainly, as well as the improved source extraction pipeline. We also apply improved selection, trying to minimize the amount of contaminants in the observed sample. So this is, again, we base this on synthetic source injections into the data. Essentially, train the neural network to predict the absolute error in structural parameters, in this case, the effective radius. So then if we say, okay, we want to say select all sources which have absolute errors less than around 20%. So we're trying to reject these catastrophically poor measurements. If you apply that thing that you train on these synthetic images to the real sample, what do you find? And actually by visual inspection, you find that actually you remove a lot of these real nuisance sources. So things like background galaxy clusters, tidal features, and halos of outer halos of brighter galaxies. All of these things masquerade as low brightness galaxies in your measurement catalog. So the sample consists of around 500 sources after we apply this selection. We find there's a bimodal population that can be split into a red and blue population, with the blue population having higher SOSIC indices in general, so being more concentrated. But a key point is that also the blue population of low surface brightness sources tend to have higher surface brightnesses systematically. And this can be explained because, of course, the bluer, they have more hot OB stars inside them, so they might be expected to have low surface brightness. This also has implications for the kind of quiescent fraction, because clearly now it's a function of your survey depth. So you have to bear that in mind when I'm discussing these results. So we have this sample of 500 galaxies. We don't know the distances. And we want to, in a few slides' time, compare with the gamma spectroscopic survey. Now, the gamma spectroscopic survey is complete for stellar masses around 10 to the 9, out to redshifts of 0.1, and it's complete for 2 stellar masses around 10 to the 10 m0, out to redshifts of 0.2. So here I try and argue that these galaxies, these low surface brightness galaxies, really are in a very similar redshift range compared to the gamma spectroscopic survey. One of the
5
easiest.
minutes left, Daniel.
Okay, thanks. One of the most direct arguments you can make is color using photometric redshifts, and this really does indicate that they are quite local. There's also a very small sample of 20 to 30 galaxies which match in the gamma spectroscopic survey, and these have redshifts less than 0.2, again pretty local. Also, if they were really outside of this range, then they would begin to break galaxy scaling relations. For example, they'd be too faint for their physical sizes. And also, you can use the arguments from the first part of the talk, these kind of empirical models, which do suggest that the galaxies will be local, given our selection criteria. Okay, so now we want to basically make arguments that suggest that we're looking at a field population rather than galaxies and groups and things like that. So again, we don't know the distances. We need to try and estimate their environmental density. Now, the key argument here is that the LSB sources and the gamma spectroscopic sources occupy a very similar range in redshift, as per the arguments in the previous slide. And this basically means that the projected separation from nearby spectroscopic galaxies should correlate with the intrinsic 3D separation. Therefore, we can estimate the environmental density by taking the average distance to the nearest k neighbors. So this introduces this k parameter. It's kind of like a hyperparameter. So at the end, we'll show that there's no dependence on this k parameter. But importantly, it's important to show that any correlation we see is actually statistically significant. So in order to do this, we make this spatially randomized population of celestial coordinates and just kind of like create random coordinates, measure the distribution of this environmental density metric, and compare that to what we get for the LSB galaxy populations. Okay, so this basically shows the whole thing. So the kind of gray histogram there is the randomized celestial coordinates. So if you just put these coordinates in, measure the distribution of this environmental density metric, you get this gray histogram. Comparing that with the blue LSBs basically shows that there is no significant spatial correlation, and that's statistical. So this really is implying that the blue population is associated with low density environments, so it are really in the field. And the red LSBs, actually, as you might expect, do show statistically significant correlation with local structure, so local gamma spectroscopic galaxies. And you can do this in either physical units in terms of distances for the environmental density metric, or angular units. It doesn't make a difference to the result. And also it doesn't, so those are the first and second rows. And in terms of columns, I showed that the result is robust against changes of in this K parameter. So you can take this one step further and try and then constrain the quiescent fraction based on this environmental density metric by calibrating essentially what you mean by the group in the field using gamma group catalogs, rejecting things which may be outside of, which are inside of groups essentially, as well as rejecting things which the photometric redshifts might suggest are outside of this redshift out to 0.2 range. And if you do this, you find after applying corrections based on the recovery fraction estimate I showed earlier, you get a quiescent fraction of approximately 25%. So this is an upper limit, again, because it's very likely that some of the redder sources in particular will be at higher redshifts, and therefore will show no correlation with local structure in any case. So these will be contaminants in the sample, raising that quiescent fraction. Conversely, as we go to lower surface brightness levels, this quiescent fraction is likely to increase, and that's because the essentially lower surface brightness galaxies tend to have redder colors. So this is an interesting point. But importantly, there is actually no dependence on this density metric, which is good, showing that the result is relatively robust here. So yeah, that's basically it. That's about 20 minutes, I think. So if you're interested in these results, then go ahead and read the papers. There's lots more details in there. And yeah, feel free to ask me questions now and send me email whenever you want. That's basically it. Thank you.
Fantastic. Thank you very much, Daniel. I'll hand over to Dorota for question time.
So we have 5 minutes time for questions from the audience. So if you have a question, please raise your hand or ask the question in the chat. Yes, we have the first question from Ilsan.
Oh.
Hello.
Hi, Dan. Thank you. Very nice presentation. I'm just curious, can you comment on how the image size impact your result in terms of extracting source by modeling GalFit, the surface brightness using GalFit? And do you find any optimal the image size?
So what do you mean by image size?
It depends on, although you said the hyper supercam has a the better pipeline to subtract the sky background, you still need a finite image size to model this, right? So depending on how you set up the outfit, depending on whether you fix the sky or you let the sky background vary.
Okay, so more detail on the yeah. So actually, to do these gal fits, what I found was it's very important to fit a inclined sky model. Without the inclined sky model, I was actually, with the synthetic sources, getting significant bias, particularly in RE and N. So yeah, the size in which you do the fitting has to be large enough, and this it's difficult to estimate this in an unbiased way. It has to be estimated from your essentially either held fixed or derived from your empty objects measurements. So I think we use the argument that we're kind of selecting things, with angular sizes less than around 10 arc seconds. So I forget how large we use the box size exactly. But essentially, if you know that what your maximum source is, you can kind of choose the box size accordingly and keep it fixed or make it smaller, depending on whether you want to try and improve the performance of the pipeline. But yeah, crucially, these plots showing that we're able to recover the structural parameters, that's the important thing. As long as those look right, then yeah, that's all we aim for.
Thank you. Sort of the 10 arc second by 10 arc second picked image size is sort of the reasonable for you to do this.
So it would actually be slightly larger than 10 arc seconds, because 10 arc seconds in the largest case, you want to be going out to a few effective radii. So
okay.
Yeah, if effective radius is 10 arc seconds, you might be looking at something like 30 arc seconds.
Yeah, because a priori, it's difficult to know the effective radii for those low surface brightness galaxies, right?
Yeah, right, exactly. Yeah, it is very difficult. Very difficult.
Okay.
But within the parameter ranges that we're looking at, it appears that with whatever settings we use, I can't remember exactly what settings we used, that yeah, it works.
Right, thank you.
But yeah, that inclined sky profile component, really important.
Yeah.
Are there any other questions from the audience?
I have a quick question, if there's no other from the audience. Well, these low surface brightness galaxies are very interesting, Daniel. Could you speak a little bit more about the secular channels by which they form? You mentioned supernova explosions, but how do you make a whole galaxy from a supernova explosion?
That's a really good question. I have to confess, I'm not a real theorist. I think the word is outflows. I'm not really sure exactly how that works. Yeah, I think for a fair answer, you should speak to a theorist on that one. But it's not just supernova channels. It's not just supernova. One of the most popular, this is probably the wrong slide. Oh, well, I don't know where the slide is. Yeah, one of the most popular explanations for these things is actually that they have large amounts of angular momentum in their halos. So this is the spin parameter. And this actually seems to be consistent with what we're seeing from kinematic analysis of small samples of UDGs that have their kind of like resolved gas. So from that, you can kind of try and get the spin parameters a little bit. And that seems to be a feasible way of explaining most of the UDG population. And importantly, it's actually completely consistent with lambda CDM. So it's actually what you expect in the kind of high spin tail of the low surface or the dwarf galaxy population. That's how you explain these large systems. Exactly the mechanism how supernova produce these things. It causes some kind of outflow, which I think kind of impacts the dark matter within the halo, somehow causing an expansion. I don't know exactly how that works. Yeah, but I can send you a reference for that if you'd like.
Yeah, great. It'd be good to know a little bit more about that. Thank you.
Yeah.
Are there any other questions? If not, I think we can start with the second speaker, and Melia will introduce Christina.
Fantastic.
you.
Well, let's thank Daniel once again for a very interesting talk. And